most of even though I'm from the University of Delft, presenting in the name of the University of Delft, most of the work that I'm representing was done at IIT, human-robot interfaces and physical interaction lab, which is led by Arash there. And also I work with Wan Soo Kim, who should be here also today, and Cheng Feng, and also from Josef Stefan, there's Jan there, that's also some work from that side. Okay, I'll start with a short introduction and motivation of the work. So, robots, why doing this human-robot collaboration? On one hand, robots have superior movement, speed and precision, but on the other side, humans have superior cognitive capabilities and are good at adapting to new situations when they arise. So what we want to do is to combine these advantages of each of the agent and exploit them to make better systems. But robots in the past were usually not capable of safe interaction with the humans or could not understand what the human was trying to do. So they would usually be put into the cages and the access to them was prohibited. So what we want to do is change them. Sometimes they were researchers trying to solve this by collision avoidance, but we don't want the robot to perceive human as a collision, but we want the robot to perceive the human as a partner to interact with. So okay, for this human-robot collaboration, first the robot has to know some basic idea of the task that it's executing. So it needs to know in which direction of the task frame it needs to control what kind of variables, for example, forces, motion, impedance, and so on. And we designed sort of a method that is able to do this. So it enables the robot to observe from the human and then autonomously derive this kind of basic idea of the task it is supposed to perform. So on the left side there's a human observation, and the robot then uses that data to autonomously derive in which axis of the task frame which kind of variable is important to control, and also can get reference trajectory from that. So when the robot has, okay, maybe there's some other examples I can show you. So for example, there was swiping here, is sawing and drilling. And again, on the left side there's a human demonstrating the task, while on the right side there's robot autonomously doing this task from the learned skill. So a lot of noise. Okay, so then when the robot has this basic idea about the task it's going to perform or collaborate with a human, then we can perform this kind of collaboration with the human, and for that we kind of need a sort of an approach to control this kind of system. So the challenges are how to do this complex interaction with the environment and the human, which has to be done many times simultaneously, and it's unpredictable. And also the robot needs to know what the human is doing, so there's some intention recognition problem. And of course, in the end, there's safety of the human, which is also important when you are collaborating with something. And also ergonomics of the human partner, so that the task can be executed efficiently and that we don't produce any kind of long-term negative effects on the human worker. So let's start with the intention recognition and interaction control. So for this kind of task, we use hybrid force impedance controller. So the robot is capable of controlling in different axes of the task frame force or impedance or motion through impedance simultaneously. And we also define some kind of method that the robot is able to observe the human arm and get the human arm Jacobian and from Jacobian we can get manipulability properties. So I don't know how many are you from the countryside I am. So, for example, if you are doing sawing, you will always align your sawing axis with the best, with the axis where your manipulability for the force production is the highest. So you will never saw in this direction, you will always saw this because you can pull easier. Okay, here's an example of the video. So just to show that with this crosscut saw, doing it alone is difficult. And here's the robot collaborating with a human. So we use the robot uses force sensor plus motion sensor, plus we have some EMGs on the human that gives the robot some extra information about the human arm impedance. So when the robot is pulling, the human can be compliant, not to oppose that motion. But when the human starts to pull, the robot can understand this and can become compliant, not to oppose the human motion. And here's this configuration interface, which the robot can use this manipulability measure to estimate in which direction the human is about to saw, and then it can adapt this kind of task frame accordingly. And also you can see that you can do it with different kind of speeds. The robot will always adapt to the speed of the human. And we have another example here. So here we use similar approach, but here we also exploit the environment. So the robot is completely compliant in translational axis. So it means it has no stabilization. But then the human can use its cognitive capabilities to find this ball that they have to turn, and we can use the environment to stabilize the axis of rotation, and then the robot can just increase the stiffness along the rotational axis, and it will rotate around the axis that's defined by the environment. So even if the human is not capable alone turning this valve, the robot can get this intention and induce enough torque to rotate this valve. Okay, then we come to when we solve this kind of intention recognition problem and interaction control problem, we can move on to the safety of the human and also ergonomics of the human coworkers. So unlike robots, humans tend to get tired quite quickly when they do some high effort tasks. So here we use the same EMG that we use for the intention recognition, but this time we also use it to estimate the fatigue of the human muscles. So through EMGs and through some model, the robot gets the fatigue of the human. And during the initial phases of the collaboration, it just follows the human, but in meanwhile, it also learns the trajectory and stiffness regulation of this kind of task. And then when the human gets tired, when the fatigue reaches some threshold, the robot can take over majority of the task with the skill that it learned in the previous stage. So the idea is that the robot can learn online from the human and can estimate the fatigue of the human muscles online. Here's another example, like polishing. So the robot is basically completely compliant in the plane perpendicular to the surface, but it has to produce the force perpendicular to the surface. First the human do it and the robot learns, and then when the fatigue kicks in, the robot takes over this force production, and the human can just then lead the robot where he wants to polish this material. Okay, we all know that DMG is really pain in the ass to use, so we prefer something more easier to use. So what we did here was try to simplify this, that instead of measuring EMG and getting the fatigue from there, we can have some biomechanical model of the human arm, and we can estimate the muscle forces, individual muscle forces. And to do this, we first use some offline methods that use some complex optimization processes to gather some training data, and then we use that training data. The training data consists of the relationship between the configuration of the arm, endpoint force, which can be measured by the robot, and then we can get the output, which is the individual muscle forces. And from that data, we use some machine learning technique to get this, to learn this relationship, and then we use this model online for the robot to predict the muscle forces, and from the muscle forces we use the muscle fatigue model to get the fatigue, and then there's some muscle fatigue management system on the robot side that influences the control in a way that it can handle this human fatigue. So, for example, in this case, when the human is polishing this object downwards, some specific muscles on the lower side of the arm will get tired. And when the robot detects this, some fatigue, then it can switch the configuration of the task performance so the force is performed in a different direction, which would involve different kind of muscles in this endpoint force production. So you can see maybe those polar graphs on the bottom right corner. So it kind of gives you a relationship between the endpoint force direction and the muscles that are involved in that endpoint force production. So the robot can know in which direction it can involve or rest certain muscles. Okay, then we have another problem. So let's say which is more immediate problem. Fatigue takes a little bit time to occur, but if you are carrying something heavy with the robot, for example, or even by itself, you will get a huge torque will get induced into the body of the human. And what we try to do here is to make the robot detect these joint torques and try to change or force the human to change this configuration through physical interaction to a more ergonomic way. So this work was mostly done by Wansu. Kim is probably is there. So he basically developed this method to estimate this joint torques. We call it overloading joint torques that would come from carrying an external object. And when we get these overloading joint torques, the robot knows in which way it has to optimize to change the configuration in a way that it will minimize this stress on the joint. So here's a nice example of the carrying task. I collaborate with the carrying. So here's Wansu carrying this heavy table, and the robot knows that there are huge torques in the initial configuration, so it tries to push him in a configuration that's more ergonomic, let's say. So on the left is with the method, and on the right is just what the robot will do to basically make itself comfortable. But we don't want the robots to be comfortable. We want humans to be comfortable. Okay, then we went further with this method. So we also introduced it into the handover. So the robot can hand over where it's most comfortable for the robot, or it can calculate this joint torque that will be induced by this object that's handed over to the human, and then brings it into a configuration that's most optimal for the human. Or we then also explore this co-manipulation task. So the robot estimates the best configuration for the human in terms of joint torques, and we also consider the the muscle manipulability of the human arm. So we also want the human not to be in a singular configuration of the arm, because there is very difficult to produce any kind of complex motion. Okay, we got this thing to the KUKA Innovation Award last year. So, and we got the best, the prize. Okay, now I'll show you something on the exoskeleton. So this method is quite simple. So the idea behind this method is that we use the EMG feedback, and we try to learn such torques in the joints of the exoskeleton that these torques will try to minimize this muscle activity. So you can see the robot learns and learns until the muscle activity is reduced, and by doing so, it compensates for dynamics of the human, dynamics of the robot, and the dynamics of the task. And you can see now the kind of the reference of the motion change, and the new motion had to be produced, and then the human just induces this extra effort needed for producing this new reference motion. And until the robot is adapting, the human still produces some effort, and then when the method learns the correct torques to produce this task, then the human can again relax, and the robot takes over. And of course, this kind of motions can also be then learned and stored, and just replay them later if we are doing the same task. Okay, then we also tested this on the whole arm exoskeleton. So here are like the muscle activity on the red. So it's on the left one is the shoulder joint, and on the right one is the elbow joint. So the motion here is a bit more complex. So because it involves multiple muscles and multiple joints. So of course, if the frequency, if you change just the frequency and you keep the amplitude the same, the dynamics change. So the exoskeleton would have to adapt to a new task dynamics. Okay, then the last reference change was upwards, and again the exoskeleton is adapting and gradually reducing this muscle activity and learning the appropriate torques that will produce this task. And then we also used this manipulability, muscle manipulability measure in the exoskeleton control. So if you have your arm really extended, your force manipulability is really bad in the direction of the lifting of this object. So you do it with more difficulty. What we try to do is to get the robot measures this manipulability, muscle manipulability of the human arm, and then adds the assistance into the joint torques, so that the force at the end point changes in a way that it's kind of simulate the manipulability at the end point like it was isotropic. So you can see now on the figure there. So the original manipulability would be the ellipsoid, would be the red one. But then when the robot adds this assistance, it kind of transforms it into this isometric one, which is blue. So this means that the human has equal force production capability in all directions of the workspace. And if the configuration change, this will also adapt. So in all the workspace, it tries to keep it circular or isotropic. So you can see the EMG was high, and now the exoskeleton is producing some assistance, and the EMG reduces a lot. So the EMG is the red one, and the assistance factor is on the top with the blue graph. So this would be really hard to lift alone, because it's close to singular configuration. Okay, human gets tired, but also a robot can get tired. Let's say if you buy a collaborative robot, usually, at least now, they don't have a really high payload. But let's say you need to produce temporary some really high effort task, which would go above the robot's specification. So we try to develop a method that would allow this. So it detects, the robot detects the thermal fatigue in the motors. So okay, the first phase is like, again, so the human teaches the force, and then when the robot learns this force that it has to produce, it takes over, and then the human can just do it. But we did really high force here, so the fatigue in the joint would increase gradually. And I think it's the third joint gets into the fatigue first, because it's kind of involved a lot in that axis. So then we use this redundancy of the robot arm to kind of change the configuration of the robot that would, let's say, remove the specifically tired joint from being involved in the main task, force production. So now the axis of that motor is pointing up, which would produce really little force in the direction of the gravity, which the tool was quite heavy, like 5 kilograms. But of course, this is done automatically by the robot. So we can see it keeps trying to change this. But of course, the limitation of this robot is that it has just one redundant degree of freedom. So if another joint gets fatigued, then you are out of options. So we imagine this more for a humanoid robot case, which has a hyper-redundant system. Yeah, I don't know why we did it so much time. Okay, and another example would be this one. So it's like Polish. Oh, no, it's not. Okay, it does the same thing. So okay, we saw before that the robot can learn from the human while collaborating. But there are sometimes there are cases when the human involvement is very difficult. For example, too many robots and too few humans to do all the learning, or the robots has to work in a hazardous environment where the human cannot collaborate with them and cannot teach them the task execution. So our idea here was that we can use a skilled robot that got the skill from the human, and then this robot can propagate the skill among other robots. So robot can learn from robot. And the basic idea is that the basic skill, like let's say this task frame definition, like I showed at the beginning, can be downloaded from the cloud, which is practically the same for all robots. But then if the robot has different specifics, there are two different robots, they have to learn this task production and actual collaboration online. So then we can do this. So here's, I think on the novice robot is on the left and the skilled robot is on the right. So in the initial stage, the novice robot is completely compliant and it's guided by the skilled robot. In that phase, it learns the reference motion trajectory. And then in the second stage, it starts to produce this trajectory. And based on the forces, it can estimate whether it should be compliant or it should be stiffened in different phases of the task. So in the second stage, it also learns how to regulate the impedance of the endpoint in order to produce this task correctly. So and then in the end, when they learn, they are both skilled. So this was it, and yeah, these are the main collaborators. Thank you.
Well, thank you very much, Luka. We have time for a few questions. With like. Yes.
I was wondering, this is about the part of your talk where it was about optimizing the posture, some ergonomics of the subject, and then this is all based on computing torques, from what I understood.
Yeah, or muscle forces and then fatigue.
But then they are, to get that information of torque on the muscular forces,
Yeah.
there are so many models that are involved that the value of what you're computing by itself is like sort of an estimation, which is probably, may have a large discrepancy between the real one to do all the model that you have been using. So usually in ergonomics, because it's easier, people observe the posture and simply the movements or the joint values. So I was wondering, why have you chosen to use this torque computation as the thing, or muscular force as the thing to optimize, instead of just watching at the posture and maybe comparing to that what is a good posture, and maybe use this as an error signal.
Yeah, I have to say that the robot has to measure the configuration of the human online anyway.
Yes,
but what you are probably suggesting that there are some from experience, there are some postures that are known to be good and some that are bad.
That's ergonomics.
But I mean, let's say you are doing some new task that was never done before. So the cost of this would be to let a guy work for 10 years and then destroy his back. And then you would know this is a bad posture. So we're trying to avoid this.
Also, the thing is, I'm a colleague actually. Interaction forces can make good postures bad and vice versa. So we need to consider interaction forces. So if you're inclining too much, if you're telling me this is not ergonomic, if I put a table so you can lean on the table, it becomes ergonomic, right? So it's the interaction that makes it,
Yes, I understand that. But the question is, what is the amount of mistake you make by using like simple references like reference posture? You make some mistakes, I agree with that.
Yeah.
But then what is the amount of mistake you make when you are doing like that simulation that, you need probably the torques with me leaning or this guy leaning, they are probably very different, so you get all the anthropometric parameters of my person, and then to even, to measure that posture, that movement, that's a very complex computation and instrumentation and parameterization, just to get something that is not that precise.
Yeah, but I mean, also car was expensive at some point, but I mean, if it becomes useful, I mean, if the robot will be like getting more and more, then also the system, okay, we use this complex motion capture system, but now you get ones that are cheaper. Okay, they are less precise, but at least you can estimate roughly whether this is a bad posture or a good posture. But we agreed, so when the better models come, we can include them in our approach. So, but yeah, at the moment, we are limited with the precision of the models we use.
Any other questions? Yes.
I really enjoyed your talk. I liked how it seemed like you learned what people were doing really well. I was wondering how you obviously have force and impedance for each task that you have to kind of specify the directions that you're trying to learn and the directions you know about. Do you see a way that you could generalize this to other things more easily, so it'd be very quick to go on to another task, so you could kind of know what parts to learn, what parts to listen?
Yeah, that's a good question. I mean, the humans have these cognitive capabilities. So we know that we did the sawing, but maybe the wiping, you know already just because you did sawing, or you did wiping already, but you know approximately what kind of forces and which direction you need to control the impedance, force, and motion, just by generalizing from the previous experience. But unfortunately, the robots yet are not that smart. And yeah, that would be a good direction to work in, but unfortunately that's not my field. I think all the deep learning in the conference should maybe focus on solving that kind of issues.
Yes.
Yep. Thank you very much for a very interesting talk. I have a quick question about the point that it was like a periodic task, and then the robot learns about the EMG and then tries to minimize it,
Yeah.
also about the manipulability. How long it takes for the algorithm to learn the behavior? Because, for example, if I'm doing a task and I want to change the behavior, if the robot doesn't react fast to what I do, it may cost me even more in terms of the EMG and fatigue and muscle work. So how long usually it takes, and like how fast you can make it in the future?
Yeah, as you see, maybe for this example, it took 20 seconds to learn one motion. I mean, the bigger range is, the more it will take, and the bigger change it is, the more it will take. But this adaptation speed can be regulated by a certain parameter in the method. But of course, we don't have a model of the system, nor exoskeleton, nor human, nor the task. So the idea is that you don't need these models, you learn them. But the bad side about this is that you cannot estimate the stability of the system. So if you increase this factor too much, the system might become stable. So it's kind of like an ad hoc at the moment, I have to admit.
Thank you very much.
Thank you.
Okay, I do have a quick question while we are changing speakers. I think it's related to the first question when you were optimizing where the robot should bring whatever it's bringing in order to reduce the torque of the person.
Yeah.
How do you make sure? Because I mean, even if I have to put my hands here, I can do like different movement with the rest of my body. So how do you make sure people actually adopt the posture that you computed as the best one? Do they have some feedback? And did you try that with like not you or ones who basically like?
Yeah. In this video we did not, and all these videos we did not. But Marta, I think maybe it's not.
Yeah, there's some point
Marta
we
worked on
provide
this.
kind of a visual feedback in the meantime. In front of the mobile, that's just right next to the mobile side, we provide the visual feedback to make sure that optimize posture. Like I said, I mean, human is a high redundant, high. So anyway, so we just provide the feedback to which one is optimized configuration. So subject or the people should try to follow this configuration of the optimized.
So you need an extra monitor.
Okay.
Which maybe now you can use cell phone or something.
Actually, so in the previous conference in ICRA, so we also developed wireless vibro-tactile sensors. So when we put on the leaves, when they are also they start vibrating, and they take you to the most optimal configuration. So either visual feedback or vibro-tactile sensors, wireless, they are the ways that we communicate depending on the rootedness of the manipulation.
Well, thank you. Let's.